everyone, welcome to our work, Provable Lifelong Learning of Representations. I'm Xinyuan from Georgia Tech. This is the joint work with Weiyang and Santosh Vempal. In lifelong learning, the tasks to be learned arrive sequentially over time in arbitrary order. While learning, knowledge from previous tasks can be captured and transferred to subsequent ones to improve efficiency. So we usually assume that all tasks share a set of common features. This is similar to the multitask learning, but in the multitask learning, we can discard the old task while only keeping the new task. In lifelong learning, however, we will take care of every task in the end. Our setting is the task-incremental binary classification. Let X to be the input space in Z dimension, Y to be the binary label space. We consider M tasks sharing K common features, where K is much smaller than M and Z. For each sample X, it's labeled as sign of AI transpose X, where AI is the target vector that we want to learn. Our goal is to learn each task sequentially, such that the maximal area of all tasks is less than epsilon. We generalize to the setting of nonlinear features in our paper. There is one data distribution assumption. We assume that for any unit vector U and V, their testing error is in the same order of the angle between them. Our assumption is actually satisfied by all log concave distributions, and it helps us to connect the test error to a distance metric. Now I will introduce our algorithm, lifelong learning with representation refinement. Our algorithm maintains a set of features. When a new task arrives, we attempt to learn the new task with the current features, and check whether the hypothesis has error less than epsilon. If yes, we can just record the linear combination parameters. Otherwise, we will learn a new set of features to solve the current task within error epsilon accurate, and then apply a step of representation refinement on all of the features we have learned. This representation refinement step is essentially finding an approximated feature subspace with the minimal dimension. But as we can see, this optimization problem is NP hard. We here provide an efficient constant factor approximation algorithm using semi-definite programming. We have proved that if the original problem has a solution of k dimension with error at most epsilon accurate, then our algorithm will output a 2k minus 1 dimensional subspace solution with error at most square root 2 epsilon accurate. Our main contribution is the sample complexity bound. We consider the lifelong learning setting with input dimension Z and tasks with k common features. We prove nearly matching upper and lower bounds on the total sample complexity. So for our algorithm, we have upper bound the number of the steps that we need to learn new features by O tilde of k. So we can upper bound the total number of the samples to learn M tasks by O tilde of D times k to the 1.5 over epsilon plus km over epsilon. The first term comes from the samples of the tasks that we need to learn new features. The second term comes from the tasks that the current features are good enough. We make comparison with the concurrent work in lifelong learning and multitask learning. From the table, we can see that our bound has the best dependence on the feature dimension k and target error epsilon. In addition, we have proved a lower bound for any lifelong learner that has black box access to a single task learner. This shows that our algorithm and analysis is nearly tight. Finally, we complement our theory with experiments. We have conducted class-incremental classification, where we learn new classes sequentially from C100. We propose a heuristic lifelong learning algorithm, where we learn a separate encoder for each task, while keeping all the previous encoders frozen. Then the algorithm fine-tunes the last classifier layer using the memory buffer and the current task data. From the left plot, we can see our algorithm has outperformed the state-of-the-art continual learning algorithms, and from the right plot, it shows that the performance of the previous classes only drops slowly and stably. This is desired in our lifelong learning setting. Thank you so much, and this is the end of the talk.